I will be presenting about the introduction for my poster that involved in developing oral insulin delivery. The oral route is the most preferred way to deliver drug because it's safe, easy, and improves patient compliance. However, delivering insulin orally is extremely difficult. This is mainly because the insulin cannot be easily absorbed through the intestinal epithelium, and it is also very sensitive to degradation by enzymes in the gastrointestinal tract. In the GI tract, oral insulin have several strong barriers. These include low intestinal permeability, high enzymatic activity, and acidic stomach condition, all of which greatly reduce insulin bioavailability. To overcome this barrier, researchers have explored a nanotechnology-based solution. One promising example is a ternary nanocomposite system, which used as an insulin aminoclay core coated with a glycosatosen and uracil S1000, also known as EGAC. This system has shown over 90% in treatment efficiency, and it releases very little insulin in the acidic pH, but provides a controlled release pH 7.4, which mimics colon condition. For this study, we are offering a suggestion that combining uracil S1000 with the FS30D also allows insulin release at pH 6.5, and the release behavior depends on the coating thickness. Importantly, improving the acid resistance of S1000 can protect insulin better without altering its ability to dissolve in the colon. Overall, this finding highlight the potential of pH-sensitive polymer coatings and nanocomposite systems to improve oral delivery.
So for this project, the main research problem is how hard it is to deliver insulin orally. The first issue is that insulin gets destroyed really fast in the stomach. The pH there is around 1 to 2, which is extremely acidic, and insulin just can survive in that environment. The second problem is that sometimes the coating releases the insulin too early in the small intestine. When that happens, the insulin doesn't reach the right place for proper absorption, so the effectiveness drops a lot. The third issue is with using the rigid S100 by itself. Even though it's meant to dissolve at higher pH, it still doesn't protect the insulin well during the early part of the GI journey. Because of that, the insulin ends up with low stability and low bioavailability. Because of all these limitations, researchers are exploring a dual-layer coating using rigid FS30D and S100. FS30D helps with acidic resistance and keeps the coating stronger, while S100 controls the release at higher pH. But the problem is there aren't many studies that compare dual layer the dual layer system to the usual single layer S100 coating. So the gap is basically what this research is
The
trying to
objective of
highlight.
this project is to formulate and characterize the single-layer uracil S100 and dual-layer uracil FS30D S100 microcapsules for the oral insulin delivery, whereby evaluating their physical properties such as coating stability and protection against the enzymatic degradation, and to compare their acid-resistant and pH-dependent insulin release profiles in the simulated gastric ileal and colonic condition to assess control release performance, whereby their pH value is around 1 to 7.4. That's the objective of our project. For the hypothesis of this project is the dual layer of uracil FS30D S100 microcapsule exhibits significantly greater acid resistance and coating stability than the single layer uracil S100 microcapsules, which reduce the insulin leakage during the gastric transit at a low pH, where around 1 to 2 pH. They also achieve higher encapsulation efficiency and a more uniform morphology, providing enhanced protection against early degradation in the gastrointestinal tracts. This results in a more controlled pH-dependent release profile that minimizes the premature insulin release in the ileum, whereby the pH value is around 6.5 of the environment of it, and enables a target release in the colon, whereby the environment is around pH 7.4, improving the overall effectiveness of the oral insulin delivery, whereby this is the hypothesis of this mini project, of the project. Thank you.
For methodology, this project will prepare two insulin microcapsule systems using pH-responsive uracil polymers. First, single-layer S100 microsphere will be produced by dissolving uracil S100 in ethanol and adding a small amount of 3-ethyl citrate to improve film-forming properties. Insulin will be dispersed into this polymer solution using magnetic stirring until a uniform suspension forms. The mixture will then be emulsified into chill aqueous phase containing a stabilizer such as PVA using high-speed homogenization to control droplet size. Once droplets form, the solvent will be allowed to evaporate gradually so the S100 shell can solidify. The microsphere will then be collected by centrifugation, rinse to remove excess stabilizer, and dry under vacuum before curing at 50 to 55 degrees Celsius. Next, dual layer FS30D S100 microfilm will be prepared by coating the S100 cross with an additional FS30D layer. The dried S100 microsphere will be suspended in diluted FS30D aqueous dilation and gently agitated so the outer layer can deposit uniformly on the particle surface. The suspension will then undergo a controlled drying, either by mud heating or air circulation, so the FS30D film can form smoothly. The fully coated particles will be sieved to ensure uniform size and cured to enhance adhesion between the two layers.
To characterize the nanoparticles, we use SEM, FTIR, and UV-Vis. SEM allows us to observe the shape and surface of the particles, confirming their formation and morphology. FTIR was used to compare the functional groups of S100, FS30D, insulin, and the final nanoparticles, and any peak shift indicated interaction that supported successful coating and encapsulation. UV-Vis was used to measure insulin concentration for drug loading, encapsulation efficiency, and in vitro release. To determine encapsulation efficiency, we extracted insulin from a known amount of nanoparticles, measured the insulin using UV-Vis, and compared the actual amount inside the nanoparticles to the theoretical amount used during preparation. For the in vitro drug release study, we tested the nanoparticles in pH 1.2 and pH 6.8 at 37 degrees Celsius with stirring, collected samples at set time points, centrifuged them, and used UV-Vis to measure the insulin release. This helped us see how the release pattern changed at different pH conditions and whether the S100 FS30D coating provided protection at low pH.